In this video, we will study conjunction, that means and, in propositional logic, and how to deal with it in the Lean proof assistant. We start by assuming that A and B are propositions. So let's make sure we haven't made a mistake. A is a proposition here, and B is also a proposition. And in the first section, the goal is to study how we can prove a proposition that is of the form A and B, provided that we have proofs of A and proofs of B separately. This is what is called the introduction rule for AND. So we assume here in lines 8 and 9 that we have proofs of A and proofs of B available at our disposal. So tiny a and tiny b are proofs of A and B, respectively. And then in Lean, there's a built-in constant called and.intro, and we can apply it to our proofs of A and B, and the result will be a proof of the proposition A and B. So if we look at this in more detail, we can see that the type of and.intro N.intro is a function, a polymorphic function, which for any propositions A and B gives us, let's do it as follows, A, B, which, so N.intro is a function that we can apply first to propositions A and B, and then it gives us a sort of a lemma or a result that allows us to prove A and B from two proofs of A and B separately. So if we apply intro A, B to a tiny a, then it shows us that all we need still to prove A and B is a proof of A. If we provide this proof of the B as well, we end up with a proof of the proposition A and B. So this add here, this is what is called, this makes the arguments, some arguments explicit here. We can write this shorter as check and.intro AB. We already had this above. So and.intro AB is a proof of A and B. This and.intro, this constant, it corresponds to this inference rule, which says that in order to prove A and B, it suffices to have a proof of A and a proof of B separately. So here the proofs of A, the proof of A was our tiny a, and the proof of B was our tiny b that we had given before. We have a short notation for and.intro AB. So these brackets here, a left angle and right angle brackets, they are a short notation for and intro A, B. Now we know how to prove, let's do this. Let's see how what this looks like in the middle of a proof. Say we are in the middle of a proof and our goal our goal is A and B. And for some reason, we have a proof of A and a proof of B. We know that A and B hold, or that we have a proof of A and we have a proof of B. How do we do that in an interactive proof? Well, we replace the underscore that we have here, firstly by and.intro, and then two underscores. And these two underscores now stand for the proof of separately of A and B. So instead of needing to prove A and B, we now need to prove A and B in two separate goals. So we can put these guys here in parentheses. Typically, these proofs will be longer. And typically for this underscore here, we will have to insert a very long proof, possibly. Here it's very easy because we have a proof tiny a of A. So we can just add A here. And here we have a proof of B that we can just insert here. But typically these expressions will be longer, these proofs of A and B separately. So we put them in parentheses so that Lean understands what we are telling it. This concludes our study of the introduction rule for AND. Let's look at the elimination rule. The elimination rule tells us what we can do with a proof of the proposition A and B. So suppose that H here is a proof of A and B. And one thing that we want to certainly do is when we have a proof of A and B, we want to prove A from it. And that can be done using the built-in constant called AND.left. So when H is a proof of A and B, then AND.left applied to H is a proof of A. Synonymously, we can just write H.left. That's exactly the same as AND.left applied to H. And similarly, we can use AND.right of H to extract a proof of B from H. So again, what does this look like in an interactive proof scenario? Suppose our goal is to prove A, and for some reason we know that we have a proof of A and B. Well, then we can just write H.left here, and the proof is done. Similarly, if we aim to prove B and we have a proof of A and B, then we can extract from this proof H of A and B, we can extract the proof of B with H.right or AND.right of H. And what we have seen is these two proofs here, or these two constants, AND left and AND right, they correspond to these inference rules, the left and right elimination rule for AND. So the left rule says that in order to prove A, it suffices to prove A and B, or read from top to bottom, from a proof of A and B, we get a proof of A. And the right elimination rule says that from a proof of A and B, we obtain a proof of B.